In this video, we're going to consider how we can find the derivative, determine the derivative of an expression which is implicit rather than explicit. So we'll talk about what that means in just a moment and do some examples. But first of all, let's consider how we could use the chain rule in a situation such as this. So we're trying to find the derivative with respect to x of y squared. The derivative with respect to x of y squared. Well, let's let u be equal to y squared. So therefore, our problem here of differentiating y squared with respect to x is really equal to du dx. And using the chain rule, we could express du dx as the product of the rate du dy times dy dx. Hopefully you can look at that and say, yep, that's the chain rule. Let's write it here just so we're clear on where that comes from. Well, du dy, the first bit there, is saying take the derivative of this here with respect to y, because that's u, and the derivative of that is just 2y times dy dx. So 2y times dy dx. So therefore, well, I guess we've said it there. Let's just put here, we could say, therefore, d dx of y squared is equal to 2y times dy dx. Now, what you might notice is that what we started off with, the derivative with respect to x of y squared, is actually just the derivative of y squared with respect to y, so 2y, times dy dx. If we wanted to sort of generalize that, then we could say, in general, the derivative with respect to x of some function of y, so of f of y, is going to be the derivative, so f dash y, the derivative of that function with respect to y, times dy dx, or using slightly different notation, d dx of f of y is going to be equal to d dy of f of y times dy dx. So it's saying just differentiate that thing, that expression, in terms of y with respect to y, and then we can multiply by dy dx. So where's all this leading? Well, this is leading us to be able to deal with what are called implicit functions, or really more often, I guess, implicit relations, or implicit expressions involving x and y. So what if we wanted to, let's do an example here. We'll say given x squared plus y squared is equal to 4, let's determine dy dx. Determine the rate of change of y with respect to x if x squared plus y squared equals 4. So looking at that, hopefully you recognize that's the equation of a circle. It's centered at the origin. Its radius is 2. And up until now, if we wanted to determine the derivative, the gradient of that curve, we would change it from the form it's in now, which is an implicit expression, into an explicit expression in y. So if I was going explicitly, I would rearrange this and say, okay, y squared equals 4, take x squared, therefore y is equal to plus or minus, and I'll use index form there since I'm going to differentiate it. So plus or minus the square root of 4 take x squared, or plus or minus 4 take x squared to the power of a half. Now that has been turned into an explicit expression in y. So y appears by itself on one side of the equation, and the other side of the equation doesn't contain any expressions involving y. It's purely in terms of x. And so then I can say, okay, dy dx, well, the derivative of this with the chain rule would be plus or minus a half times 4 take x squared to the negative a half, and then times what? The derivative of 4 take x squared, which would be negative 2x. So I guess I could simplify that to say plus or minus x times 4 minus, x squared to the negative a half, or if I wanted to put it back in surd form, I could say. Alright, so there's the derivative if I do that explicitly. But if I want to do it implicitly, which means leaving the equation in the form that it's in that form there it is expressed implicitly. So x's and y's are mixed up on the same side of the equation. In this case, they're not being multiplied together, so they're not within the same term, but we could certainly consider cases where x's and y's are even within the same term as each other. So if I'm going to do it implicitly, I'm going to use the sort of theory that I came up with over here, that I can differentiate anything with respect to y, with respect to x, by just differentiating with respect to y first. There it is, and then multiplying by dy dx. So if I'm going to do it implicitly, I'm going to say the derivative with respect to x of the left-hand side is equal to the derivative with respect to x of the right-hand side. Whatever we do to one side of the equation, we do the same to the other side, and it remains equal. I could split this up, even a little bit further. I could split this up a little bit further to say the derivative of x squared plus the derivative with respect to x of y squared. Well, the derivative with respect to x of any constant is just 0. Now, the derivative with respect to x of x squared is 2x. The derivative with respect to y squared, the derivative with respect to x of y squared is 2y times dy dx. That equals 0. So then just a little bit of rearrangement would give me 2y dy dx is negative 2x, and divide both sides by 2y, and I would get negative x over y because the 2's would cancel. So there's another way of expressing the derivative. And if you look at those two, the first thing you might say is, but hang on, this derivative should be the same as this derivative because they're both differentiating the same expression, the same relation. And you are quite right, they should be the same, and in fact they are the same, because if we were to substitute in this here, y is equal to plus or minus 4 take x squared to the power of a half in here, which is really just plus or minus the square root of 4 take x squared, then we would in fact have that as the denominator, and the plus or minus would mean that we've got a plus or minus, just like that one there. So this one here, the derivative is sort of implicit as well. It's in terms of x and y. Here the derivative is explicit. It's just in terms of x, but in fact they are equivalent to each other as derivatives. Now in that particular case there, we could have changed our implicit expression to an explicit expression and then differentiated that way. But there'll be times where we can't do that, or it's certainly not straightforward. And so in those cases, we won't be faced with this choice. We will have to say, let's differentiate implicitly. So let's do maybe just one example like that. So there's one in your exercise here, and it looks something like this. It's got the expression y to the power of 5 minus x times sine y plus 3y squared equals 1. Now, if you look at that, then hopefully you can see that it would not be easy to change into an explicit expression. In other words, you couldn't easily make y the subject of that equation there. So what we're going to do is differentiate implicitly. What I want you to notice is that this middle term is actually a product of x and sine y. So we're going to treat that one, we're going to use the product rule. So this one's sort of stepping it up in terms of complexity quite a bit. We're going to use the product rule where u is equal to x and not y. U is equal to x and v is equal to sine y. So it's u times v. So when we think about our product rule, derivative of u times v is u dv dx plus v du dx, isn't it? So we'll need to use that there. Alright, so determining the derivative, we're saying differentiate y to the power of 5 minus the derivative of x sine y plus the derivative of 3y squared equals the derivative of 1. Alright, so for the first term, well, differentiating y to the power of 5 with respect to y would be 5y to the power of 4, and then that'll be times dy dx. This one here, well, let's think about what we've got if we use our product rule. So it's going to be, well, we could take the derivative with respect to x of u, so du dx times v, and derivative of x with respect to x is just 1, isn't it? So that would just be sine y, and then plus, so we've done v du dx, now we're going to do u dv dx. So u is x, and then we're differentiating sine y. So let me write it over here. We're taking the derivative of sine y with respect to x. So that's going to be the derivative of sine y with respect to y, which is cos y, times dy dx. That's our chain rule there. So it's going to be cos y dy dx. And then we've got to differentiate this term here implicitly. So the derivative of 3y squared with respect to y is 6y. That one will get a dy dx. And the derivative of a constant is 0. So let's gather all the terms that have a sort of factor of dy dx in it. So the first one does, that's a 5y to the power of 4. This one here has a dy dx, that's minus x cos y dy dx, and then plus 6y dy dx. Minus x cos y and plus 6y, so all of those have a factor of dy dx. The only term on the left-hand side that doesn't have a factor of dy dx is this minus sine y. So if we take that to the other side, it's going to become plus or positive sine y, isn't it? So therefore, dy dx will be equal to sine y over all of this here. 5y to the power of 4 minus x cos y plus 6y. Well, there's one that we certainly wouldn't have been able to do explicitly, but we can find the derivative implicitly.